We begin our discussion about sequences, which themselves will lead us up to the main concept of series that will be a theme we explore this entire semester. In the end, series, we'll be able to represent functions using series and have even further, deeper understanding about functions like cosine and exponential functions, and be able to recognize that we could represent those as the sum of infinite polynomials. But to get there, we've got to start at the foundation, which is sequences, a concept that you definitely should have seen before. A sequence, you could think a sequence is, a list of objects. Typically in math, it's going to be lists of numbers, but it could be lists of words, red, white, blue, so on and so forth. A sequence is just something that is ordered as a first, a second, a third element. It doesn't have to be a number. It can be anything that is a list. Now, for our purposes, like I said, lists or sequences will be of numbers. So it could be a number with a pattern. It could be a sequence of random numbers. It actually doesn't matter. But for our purposes, a sequence, we'll think of it as a function that takes the natural numbers n to the reals. So this is definitely a case where we are thinking about our elements in our sequence to be numbers. But notice, we're going from the natural numbers. How do we do such a function? Well, the value of 1 would be the first element of your sequence. Value of 2 would be the second element, and so on and so forth. And so it gives us a very natural sense then to ask about, what does a sequence converge? I've got a list of things as my function, as the input's going off to infinity. If I'm going further down the list, does the series converge? And we can look at it as a epsilon delta, if you remember that back from calculus, but honestly, we're just looking at a limit, right? So we're talking about in a sequence, what happens as the index goes to infinity? Does this sequence, if it reaches a number, we say the sequence converges. If it doesn't reach a number, then the sequence diverges. Okay, so let's consider this particular sequence, 1, 1, 2, 1, 3, 1, 4. And I want to know what is the function. Remember what I said? I said that when we talk about a sequence, there should be some mapping that takes the numbers, the natural numbers, 1, 2, 3, 4, forever. So that itself is a sequence, and takes it to my list of values. So this would be A1, A2, A3, and so forth. And so in this case, A1 would be the first one, A2 is the second one, A3 is the third one, A4 is the fourth one. And I hope you can see exactly what the pattern is. I've made this pretty straightforward. What's going on? Well, if I think of this as a 1 over 1, then really it's here are the n's. N is 1, n is 2, n is 3, n is 4, and the top is constant. So I'd say that an is equal to 1 over n. That's the pattern that we've got going here. Now, does this sequence converge? Well, that's a question about a limit. So does the limit as n goes to infinity of a sub n exist? Well, that's the limit as n goes to infinity of 1 over n, and I hope you recognize that this is going to 0. So yes, it does converge, and in fact it converges to the number 0. All right, let's look at another example here. So here's another sequence. 1, 1, 2, 3, 5, 8, 13. Now this is not nearly as natural. Again, here's the first one, here's the second one, here's the third, fourth, fifth, sixth, and I don't see a direct, like I had before, that there's this number is involved. I mean, 3 is maybe 4 minus 1, but now 5 is 5. 8 is 6 plus 2. Yeah, just a quick look, I don't see a lot of relationship, but I can notice something here, that 2 is 1 plus 1. And 3 is 2 plus 1. And 5 is 2 plus 3. And 8 is 3 plus 5. And 13 is 5 plus 8. So it looks like this value is dependent on the value of the previous ones. And so I would argue that a sub n in this example is a sub n minus 1. So I'm going to go, so if I'm at the 7th one, I'm in spot 7, I want to know its value. I would look back to the value right before it, a sub 6, and a sub 5. And so a sub n minus 1 is one value below, and then two values below would be a minus 2. And now this is what's called a recursive definition. And if I've ever got a recursive definition, I've got to make sure what my starter is, because this pattern would not work for these two because I can't look backwards two values. But I can tell you that a sub 1 is 1 and a sub 2 is also 1. And now I've got I like to think of this like the primer. This is what starts everything. And once I have the first two values, that's enough to give me what everything else is here. Now, same question, does this sequence converge? And hopefully you can see, oh, heck no. This series is going to go off to infinity. I'm just adding two consecutive positive numbers, which is always going to be bigger than what I started with. So no, it doesn't. The limit as n goes to infinity of a sub n is itself infinity. So it does not converge. Here's a very nice theorem about sequences this is not the theorem yet. We're going to get one in a second. I need some definitions. We talk about a series increasing, which was exactly what the previous sequence was. It was every element was bigger than the previous one. So its sequence is increasing if, exactly, a sub 2 is bigger than a sub 1, a sub 3 is bigger than a sub 2, so on and so forth. Sequence decreasing, well, just the opposite. If a sub 1 is the biggest and a sub 2 is less, and so on and so forth. And if a sequence is purely increasing or purely decreasing, we call it monotonic. And we'll see why we don't really care which direction is because of the next page. Again, sorry, I keep getting ahead of myself. One more definition. Being bounded, again, this should be intuitional. We talk about a sequence being bounded means that every element in the sequence, if it's bounded above, is smaller than some fixed number, and it's bounded below if they're all bigger than some fixed number. So finally, let's get the theorem I keep promising. Every bounded monotonic sequence is convergent, right? So if it's decreasing and it has a bound, and it's bounded, then it has to converge. And kind of why should that be? Well, if I've got my sequences, I'm just going to kind of order them and say this is a value of a sub 1. Like maybe I'm looking at the y-axis, I'm looking at that way. So maybe it's 10 and 9 and 8.9 and 8.7. And my values keep decreasing, but if they have some minimum, well, then they can't decrease past that value. That doesn't mean it converges to that value, because that may not be the largest minimum, but it means that my sequence cannot push past that threshold. So the decreasing and a boundedness on it forces a convergence on it. Now, of course, that's not a proof. That's kind of a heuristic for why you should understand why that theorem should be true. We'd have to get into epsilons and deltas to prove this theorem, and I don't think it's very beneficial to us. It can be done, but this is enough that if it's bounded and monotonic, then it has to converge. So let's take a look at a sequence like this. So first off, what is the mathematical representation of the nth element in the sequence? Well, at first blush, you might look at this and go, this is really weird. I got a bunch of nested roots. I mean, hopefully you can see what the next one is going to be. It's going to be square root. So this is the first one, second one, third one. The next one's going to be 2 root 2 root 2 root 2. Right? So instead of having, so in the first one I have 1 root, and the second one I have 2, a root nested in a root. The third one I have a root nested in a root nested in a root. Fourth one I got a root nested in a root nested in a root. So we can see that there's this pattern. Hopefully you see it. If I wanted to represent it, probably the most natural way I would think about it is notice that this element right here, the previous one, is sitting inside of the next one. It's sitting right there. Just like this element here, the root 2 is sitting right there. And even in fact, the very first one is there as well, right? Root 2 is sitting right there. So this sets itself up, I think, for a very natural recursive definition, where I'd say a sub 1 is equal to square root of 2, and a sub n plus 1 is equal to square root of 2 a sub n. The 2 times the whatever the previous one. So that would be, to me, a very natural definition. We may see in a second it's not the best one, but it's the one I would start with. And so, question, does this sequence converge? Well, now I want to look at, that is a limit question. In fact, I want to know, what does it converge to? And here's where, I know the answer to this, I've done this, but let's say I didn't, and I wanted to have some intuition. I don't know. At first thought, it may be that I keep getting bigger, or seems like I'm getting bigger, and so because I'm whatever the previous one, I'm multiplying by 2 and taking the square root. So I know that there's some increasing business here, right? So if I kind of think about this way, right, that how do I say it? That square root of 2an looks like, now it might not be, we'd have to do some algebra, but it looks like this is bigger than the previous one. Again, I'm not saying this as a fact right now. I just saying it appears to me that that's probably true. That this is true, and I'd have to kind of work out the algebra for why this is. And in fact, I can. I could say that, well, this is true if and only if 2a sub n is bigger than an squared. And that's true if and only if, so let's bring this over, 0 is bigger than a sub n squared minus 2a sub n, or if I look at that, that's 0 bigger than a sub n minus a sub n minus 2. Now, we know the a sub n's are always positive just by construction. I keep taking radicals, so they're all going to be positive. So the only way that this value could be negative is if a sub n minus 2 itself is less than 0, which would mean that a sub n is less than 2. So is that true? Well, I know the first one is, but then as I start multiplying, do I possibly go past 2? So now I'm kind of at a place where I really want to do maybe a little bit of experimenting. Let's go over to Excel and play with this sequence. And again, this is just give me some intuition. I don't want to waste my time trying to prove this converges if the experiment shows that it doesn't. So let's come over to Excel, and I'm going to build up this sequence. So this is going to be my n values, my a sub n values. This is 1. This is equal to square root of 2, right? That's the a sub n. Now, if I go to 2, what is that? Well, that's equal to the square root of 2 times the previous value, which is the cell right above it, right? So if you never use Excel, this is great for sequences because I can recursively pull in values that are already been computed. And so this cell, which is B is the column and 2. So I just clicked that value. It's 2 times that. Compute the square root. It's 1.68 blah, blah, blah. So then, and I'm going to build this up. So this is equal to 1 plus, this is just for my own purposes. Now I can see as I scroll this down, what am I doing? Well, I'm telling it to use this formulation. So remember the formula here was, this is just my n. So just look at the previous one, adding 1. That's a incrementally growing. This one though says, look at the previous cell, multiply it by 2, and take the square root, no matter where I'm at. So look how it updated it. Now this is telling me to look at B8, the one right before, right? Okay, so pardon me to any of you who are experts in Excel, that wasn't needed, but I know there's lots of students who've never played with Excel. So, and it's a wonderful tool. And as I roll down, well, look what happens. Looks like 1.9, 1.9. I mean, in fact, this is very suggestive that the sequence converges to 2. Not a proof, because I only went to 69. Maybe way out, it does something really weird. I don't know. Maybe it passes past 2 eventually. So this is suggestive that 1, every term is less than 2, and that it converges to 2. So now that gives me some heart. So now let's go back and play some algebra with it with some confidence of what's going on. Let me just clear this board. So I know that, like I said, my a sub 1 equals root 2, and this is a perfectly good definition. A sub n is equal to square root of 2 a sub n minus 1. And is there a other way to think about this? So I know that a sub 1 is equal to 2 to the 1 half. All right. A sub 2 would then be, so it's going to be 2 times 2 to the 1 half, all raised to the 1 half, which is, 2 times 2 to the half is 2 to the 3 halves to the 1 half, which would be 2 to the 3 fourths. Okay, that's interesting. Notice I don't have it's not recursively defined back to A1 anymore. In fact, I've got it straight related to a power of 2. Let's try A sub 3 and see if this pattern continues and see if we can discover what the pattern is. A sub 3 would be 2 times the previous one, which now we know is 2 to the 3 fourths, raised to the 1 half, which would be, what is that? 2, so 3 fourths plus 1 is 2 to the 7 fourths, and that's raised to the 1 half power, which is 2 to the 7 eighths. All right, I think I see what this pattern is, right? This is 1, 2, 3, 4, 7, 8. So now, okay, the difference between them is just 1, but what's the pattern? Well, look, it's all powers of 2 in the denominator. 2 squared, 2 cubed. Just make sure the next one's going to be the same thing. Let's look at A4. That's going to be 2 times 2 to the 7 eighths to the 1 half, which is, so 7 eighths plus 1 is 2 to the 15 over 8. That's all raised to the 1 half power, which is 2 to the 15 over 16. All right, that seems to convince me that A sub n, so this is one way to write it, but I don't need to be recursive, and this happens sometimes, that A sub n is equal to 2 to the, well, what's in the denominator? And the denominator is 2 to the n, and the top is 2 to the n minus 1. That's getting a little dark. Let's write that again. So 2 to the n minus 1 over 2 to the n, right? So there's our power. Let me clean this up so I can have some room here. So what does that tell me? Okay, well, then this actually makes it quite clear that my function is increasing, but always less than 2. Therefore, it converges. How do I know that? Again, because I have that what do I say that that 2 is always less than a sub n, because it is equal to 2 to the how can I say this, 1 minus 2 to the minus n. Hopefully that you can see is definitely less than 2, and that's always bigger than 0, so it's bounded. And we can see that a sub n is going to be bigger than a sub n minus 1. So by the previous theorem, the series converges. Now the question is, where does it converge to? And now that we've got it in this form, it's pretty obvious. The limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of 2 to the 1 minus 2 to the minus n. And as n goes to infinity, this is going to go to 0, right? Because this is to a negative power. So this is equal to 2 to the 1 minus 0, which of course is 2. So not only did we use the previous theorem, which would have been enough just to answer that it converges, but we can even go to the limit and show that it converges to the number 2, which was what our Excel workbook suggested but did not prove. Now we've proven it mathematically, that the convergence of this sequence is the number 2. How about this sequence here? So what's going on with this? What is a mathematical representation? So this is not nearly as complex as the previous one. We can see 4, 5, 6, 7. So the denominator seems to be growing in just steps of 1. The numerator is growing in steps of 1. And I've got just a negative number here. So what would be my value? My a sub n looks like it'll be, so if we're starting at n equals 1, right, the top's going to be an n minus 1. Right, that's if this is the first one, this is the second one, this is the third one, this is the fourth one, this is the fifth one. Hopefully you can see, yep, my numerator is just 1 less than my index. And what about my denominator? Well, my denominator is 2 more than my index. So it'll be over n plus 2. But I have this feature that I've got a minus, so this would be minus n minus 1, or maybe more naturally distribute it through. That's 1 minus n over n plus 2. There's my sequence representation. Pretty straightforward. It's very direct. It's not recursive. Does this sequence converge? Well, let's take a look at the limit. I mean, we can look at the limit or look at it that this is definitely decreasing. Right, 1/4 is bigger than, or negative 1/4, sorry, is bigger than negative 2/5, is bigger than negative 3/6, and so forth. So it's decreasing. It is always less than 0, but it's going to be down here, right? 0 is going to be the biggest value, and then we're decreasing down below. But the lowest value, we'll notice that the numerator is always smaller than the denominator, so this is always going to be bigger than negative 1. And now we know for a fact, yes, that is a monotone decrease, decreasing isn't, monotone bounded. So yes, it converges. Of course, the next question should be, what does it converge to? And now we can see if we can get there by a limit. We won't always be able to know, but in this case, if I look at the limit as n goes to infinity of 1 minus n over n plus 2, so this is infinite, so I'd say this is the limit as n goes to infinity. Let's factor an n out. That's n times 1 over n minus 1 over n times 1 plus 2 over n. and my ends will cancel. So I get cancel, cancel. This value is going to 0. This value is now going to 0. And so this whole limit is equal to negative 1 over 1, aka negative 1. So it does converge actually down to its lower bound, even though there is a significant difference of 3 integers, a difference of 3 between the numerator and denominator. It's still, as we go to infinity, they get close enough, relatively speaking, that it converges to the negative 1. All right, so those are examples for sequences. As promised, these are really just the building blocks for discussing a more important, but at least more relevant to us in this course, and that's the idea of series, which is what happens when we add up all the elements in a sequence. But we'll save for that to the next chapter or section.